So now we're going into a density example. Population density may not be the first thing that comes to mind when you think about density, but these kinds of problems work in a very similar fashion in that in these problems, you're normally trying to find the total population given a function that represents density. When you're talking about the physical characteristic density, you're doing this in order to find the mass. As we know, density is equal to mass over volume. So in order to find the mass, you just have to multiply by volume. In this case, we have something really similar in that the density is equal to number of people per unit area. So what we need to do is calculate the area in order to find the number of people. And, wow, oh wait, we already did that, which is great. So now we have the tools we need to be able to do one of these problems. So we have a town, a circular town, with a population density described by the function density equals 10,000 times the quantity 3 minus r people per square mile at a distance r from the center. So a few things that we can gather from this model is that, like I said, we have a circular town that is most densely populated at the center. When r is 0, you have the most people, and when r is 3, you'd have 0 people. If you put 3 into that function, 10,000 times 3 minus r, you'd wind up with 0. Therefore, the radius of this circle is 3. We need to make sure that each slice has to have an approximately equal density everywhere. So, what we have going on and this ring here is going to be your slice. As the radius of this ring goes to 0, you have that ring that has an even population density all along it. Like there's no change. And this involves a very specific formula that once you get, you can remember it, but I'm going to derive it for you right here so you can think about how this works. What we're going to do is just find the area of the ring. So what we can do is subtract. If this distance is r, and r is the radius of the outermost circle, and right here looks kind of similar, but now we're talking about the thickness of this ring slice. This is going to be the thickness delta r. The area of the circle is just going to be equal to pi r squared, so we can write that. It's pi r squared and then we're going to subtract the center circle, pi times r minus delta r squared. As you can see that once you subtract delta r, you can look at it from over here. Once you subtract delta r from r, you wind up with the radius of the inner circle that is being cut out. What we're going to do is simplify this expression that we came up with that equals the area. So pi r squared minus pi times r squared minus 2r delta r plus delta r squared. This equals pi r squared minus pi r squared plus 2 pi r delta r minus pi delta r squared. The interesting thing is that this term right here will cancel because it's going to be so tiny anyway. We kind of really just don't need it. Like, delta r is already really small, so squaring it is just going to make it really tiny, so it's kind of going to be negligible. We'll just ignore it and get rid of it. So the area is going to be equal to 2 pi r delta r. And that's it. And that's going to be the area of one of these rings. So now we take our next steps. We multiply it by the density to get the population. The population on a specific ring is going to be equal to 2 pi r delta r times 10,000 times 3 minus r, and we sum that up to get the population over the entire region, and then we let delta r go to 0, and then we get our definite integral, which is going to be from the lowest radius 0 to our highest radius 3. We don't want to, like, I don't know, like add negative people or something crazy like that. And that'll just be 10,000 times 3 minus r times 2 pi r dr. And we evaluate that, and that is going to be our total population. The formula that I was talking about is specifically the 2 pi r delta r. That's going to be key when you're doing population density problems like this. It's going to come up a lot. It's helpful to remember it, but this is one way of deriving it. There is another way to derive the expression that you should probably memorize, and that's turning the ring into a rectangle. So let's try that too. So we'll draw in the specs again. This white right here is delta r. The outer edge of this ring is going to be equal to the circumference evaluated at r. 2 pi r. So when we lay this out, you have your rectangle of width delta r and of length that is approximately 2 pi r. So the area of this shape is length times width, that's 2 pi r delta r, which is the same as what we got in the other method of doing this. So you just do the same Riemann sum and come up with the same definite integral to come up with the same answer, because this is the same problem. But there you have it. And this is how you use slicing to calculate volumes and density. Later.